Okay, so we have two topics to cover. First one is line integrals of vector fields, and then we will do so-called Green's theorem. So last time we studied uh, line integrals of scalar functions. It was like this. Suppose we have a, parametrized curve C with parameterization, let's say RT, T from an interval AB, and a function f of three variables, let's say x, y, z, defined on C. Then the line integral of f over f ds is defined to be the following. So this is just the integral from a to b, f of rt, and then ds is just norm of r prime t dt. So this is our ds. And what you do, suppose this is your curve defined on this interval AB, and it is maybe something like this. Okay, this is f of A, this is f of B, and at the point RT, not sorry, RA, RB, ds is arc length element. ds is arc length element. Norm of the velocity vector, right? Velocity vector is this r prime t. ds is just norm of that times dt, and then you just multiply this gadget by the value of f at this point, and you sum them up. So this may be considered, for example, as the mass of this wire. Okay, if f represents the density. Okay, if f is the density, then you multiply density with the arc length, so you get the mass of this segment here, and then you add them up, so you get the mass. So last time we studied this. Today we will do something different. Today we have again a parameterized curve, a piecewise smooth parameterized curve C with parameterization, let's say RT, again defined on some interval AB, and a vector valued function f x, y, z defined on this curve C. Okay, and then we would like to compute the integral. So suppose this is our curve, okay, part of the curve, and at any point RT, we have this vector, tangent vector, which is just r prime t. Okay, and suppose that you are pulling an object on this curve via this via the force given by F. So F is the force, let's say. It has three components. Let's say F1 XYZ, F2 XYZ, and F3 XYZ. Okay. T is the tangent vector, and F is the force you apply to this mass. Okay. And you are just pulling this object over the curve C. Then what is F times the velocity? F times velocity is just uh, the uh, force times velocity is just the power, right? Uh, so uh, F dot product, let's say R prime T dt, say T represents the time. This is the uh, power uh, the work, the force F uh, okay, causes or produces. Why is that? Because what is the work done? Work done is just F times right, the uh, line segment you uh, the object travels, right? You take the dot product, uh, and what is this? This is just norm of F times norm of the vector times cosine of the angle between them, right? This angle. So this is just what you do. You take the component of of the force, right? This is T. This is, let's say, F. You have the component of your force uh, parallel to the rod, which is T, and perpendicular to the rod. And this gadget is just the force, the component of the force parallel to the tangent vector or to the rod. Therefore, this is just the work done during the time dt, right? The work done during a time interval is just the power, right? Bir saniyede yapılan iş nedir? Gücü verir, değil mi? Bu da işte dt anında yapılan işi söylüyor. Kuvvet çarpı yol, right? This is work times the distance traveled times dt. So this is just the power or the work done during the time. So dv is just the work done during the period dt. Okay, this is a very small time interval, and work this thing d omega is just the work done. dw is just the work done during that time. Okay, so integral of that, hence the integral of dw which is f dot. So here, of course, inside f you have rt dot product with r prime t dt over the interval AB is the work, is the total work done uh, by the force F uh, along the path C. Yani şuna bakıyoruz. İşte A to B F R T dot product R prime T dt. So this is the total work done by the force F pulling this point particle along this path, right? So this is the tangent direction, and this is your force. Okay. This force, of course, changes from point to point. T also changes. This is just the work done by F during this, uh, period, pulling this object from this point R of A to R of B. And we denote this integral like this. We write this is the uh, integral over the curve C of f dot dr. Okay, so we write it this way. Here, of course, dr means what? This is just r prime t dt. Okay. So you see, this is quite different than integrals of scalar functions, right? Scalar functions were like this. You have a scalar function, and you take just the norm of the velocity vector. This is just speed. Speed times ds is just the distance traveled by the object during the time dt. It is just this arc length, and then you multiply this arc length by this value of the function, which is the scalar. So this is not work. This can be considered as the mass, right? If F represents the density. But here, uh, F is the force, let's say, applied to this object, and uh, F dot dr is just the component of this F parallel to the tangent vector, and then you integrate it over the period AB, right? Suppose t represents the time, so time from starts from A and ends at B, and during that period of time, you pull this object from the point RA to RB, and you make a work, right? And the work done is just this integral, and we simply represent it, denoted by this notation. So this notation means just this integral. Tamam mı? Sorusu olan var mı? Siz fizik görmediniz tabii, değil mi? Yani bu fizik dersinde de söylenen bir şeydir muhtemelen de. Yani şöyle bir notation daha var. Another notation. Let me also give that. So RT is just, it has three components. Let's say XT, YT, ZT. Therefore, uh, dr is just x prime, or dr over dt x prime y prime t z prime t, or I can write it like this, as we have done already, x prime t y prime t, or okay, all right, first let me write it this way, z prime t dt. But then you see dx dt is also x prime t, meaning that dx is just x prime t dt, and so on. So x prime t dt is just x prime t dt, y prime t dt, z prime t dt, and we write it this way. So x prime t dt is just dx, y prime t dt is just dy, z prime t dt is just dz. Therefore, this integral f dot dr is also f1, f2, f3 dot product with dx, dy, dz. So it can be written like this: f1 dx, this is just usual product, not dot product, f2 dy plus f3 dz. Therefore, the integral over c f dot dr is also written like this: f1 dx plus f2 dy plus f3 dz. Okay, they all mean the same thing. The different representations of this integral. Okay. Efendim? Burası mı? Tamam. Şimdi okay. Örnekler yapalım. How we will integrate, I mean, this gadget is just this, okay? You just take this dot product with f, and then you take with integral with respect to dt. But this integral can be given like this, or sometimes it is given like this, okay? So they mean the same thing. Now let's see some examples. So this is actually not the three-dimensional version, but two-dimensional version of it. So of course, I can just take a plane curve and just work with x and y. Take z component to be 0, okay? Then this will just disappear. So everything works same way. So suppose this is the vector field. If I write in parentheses, the first component is y squared, the second component 2xy. Or if I write it in f1, f2, so f1 xy is just y squared, and f2 xy is just 2xy, okay? And C is the curve in the plane from 0, 0, the origin, to 1, 1 along. There are three parts. First one is the straight line y equals x Part B, so this is another question. The curve y equals x squared, and part C is the piecewise smooth, the piecewise smooth path consisting of the straight lines from 0 0 to 0 1 and from 0 1 to 1 1. So we are asked to compute actually three different line integrals. Okay. Solution. The vector field is the same but three different paths. Okay. A. So first of all, fxy was what? F1, F2, and this is just y squared and then 2xy. Okay. Now, the first path is the line segment. So it's the line segment y equals x from the origin to the point 1, 1. So you start from this point and you go up to 1, 1. Okay. So it is this curve. Since it starts from this point and at this point, I put this arrow, okay, and this is my curve C. Well, I need a parameterization for this curve. Well, RT, so it has two components. It will have two components, XT and YT. How can I choose the parameterization? Well, I can just let this to be T. Then what is Y? Well, X and Y are just the same, right? X and Y are the same. So this is also T. And T from where to where? It should start from the point 0, 0 and end at the point 1, 1. So I can just choose my interval to be the interval 0, 1, right? This is a smooth parameterization. So my RT is then, RT is just TT, okay? What about R prime T then? So this is X prime T, Y prime T, dt. What are the derivatives of these gadgets with respect to t? Well, they are just 1, 1, and then I have dt. Okay. So my integral over the curve C, f dot dr is then what? Well, this will be integral over t. T goes from 0 to 1. And then I have f. F is just y squared 2xy dot dot dr. Dr is what? Dr is just, okay, isterseniz bir daha şöyle yazayım. This is f dot r prime t dt, right? So this is 0 to 1. F is just uh, y squared 2xy. Dot product r prime t. R prime is just 1, 1, and then I have dt. So this is just 0 to 1, y squared plus 2xy dt. Of course, what is x and y? X and y are both t in this, parameterized curve. So I just plug t for x and t for y. So we get t squared plus 2t t squared. No, 2tt, right? Both x and y are t. So I have this. What is this? This is just 0 to 1, 3t squared. So this is just t cubed, uh, and this is just 1. Okay. So this is the work done. Work done uh, by this force F. Uh, and this is the work by done while you just pull this mass from this point to this point along this path. Okay. Yani şurada bir kütle var diyelim. Siz buna F kuvveti uyguluyorsunuz. Bu noktadan buraya çekiyorsunuz. Bu kuvveti uygulayarak yaptığınız işin miktarı bir birimmiş. Okay, now we will repeat the same for a different curve. Part B was okay. So again, I am going from 0, 0 to 1, 1. But this time, along the curve y equals x squared. So I need a parameterization RT, which is xt, yt of this curve. I may let again xt to be t. Then of course yt will be what? Yt is just x squared, right? This is x squared, so this should be t squared. So rt is just t comma t squared. So this is just okay. So it is this, and what is dr? Dr is just r prime t dt. So this is just 1 comma 2t dt, right? Therefore, the work done over this curve, isterseniz bunlara isim vereyim de ben. Bu C1 eğrisi olsun. Suppose this is C1, C1, and let's say this is C2, okay? Another parameterized curve, C2. F dot dr. Again, t is from 0 to 1 because here I am at the point 0, 0, and here I am at the point 1, 1. So t should go from 0 to 1. So 0 to 1. F was y squared and 2xy dot dr. Dr is just 1 comma 2t dt. All right, so this integral f dot dr is just 0 to 1. I can substitute t components of t corresponding expressions in t for y, x, and y. y was t squared, so y squared is just t to the power 4 comma 2t and t squared, right? And then I have dot product 1 comma 2t, and then we have dt. All right, so what is this? This is integral from 0 to 1. If you multiply this out, you get t to the 4 plus this is 2t cubed, another 2t, so it is 4t cubed. Okay, no, 4t to the power 4, and then I have dt. So this is just 0 to 1, 5t to the power 4 dt. This is just t to the power 5, 0 to 1, and again this is just 1 unit. So the work done is again 1 unit. All right. And part C is this time we have this curve. So 1 1 0 0 0. So this curve C3 has two parts. Right, it has two parts. Let me call this one C3, let's say A, and this is C3B. So this curve C3 is the union of C3A union C3B. I first go along the curve A and then along the curve B. I need to parameterize these curves separately. So what is C3A? Well, here uh, x coordinate is always 0, right? Because you are going along the y-axis, and y coordinate goes from 0 up to 1. So I can just let yt to be t, and this is t from 0 to 1. So let's say this is r1t. What is this? So this is xt, yt. So it is 0 comma t. Okay, t from 0 up to 1. And C3b is what? Here x is going from 0 up to 1. So I can just choose xt to be t. And what is y? Y is constant and it is always 1. And again, I can just choose t to be a point in interval 0, 1. So R2t, let me write this as R2t. So it has x coordinate t and y coordinate t. Okay. Ya da şöyle yazayım. xt, yt. So it is t comma 1, again t from 0 up to 1. Okay. So here I have R1 and here I have R2t. Okay. All right. Now, what is the work done? F dot dr. Well, this has two parts. So over A F dot dr plus over B F dot dr. For these two integrals, dr will be different, right? Here, this is integral from 0 to 1. F was y squared and then 2xy. What is dr? Well, okay. This is, okay, let me write it this way. R1t is just, R1t neydi? 0 comma t. 0 comma t. That's why dr1 is just 0 comma 1 dt. So here, this is 0 comma 1 dt plus 0 to 1. F is the same. It is y squared 2xy dot product dr. Well, r2 is t comma 1. So what is dr2? It is 1 comma 0 dt, right? You just take derivative. So this is 1 comma 0 dt. All right. So this is just 0 to 1. But here I have to also plug x and y. correctly, this is the curve A, C3A. C3A has, this is the x coordinate, this is the y coordinate. And for the second curve, this is the x coordinate, this is the y coordinate. So here, y coordinate is just t. So this is t squared, and then 2xy, which is just 0 because x is 0. Dot product 0, 1 dt plus here y squared. Y is just 1. So it is 1 squared plus 2xy, which is just 2xy, which is just 2t, 1, 0 dt. Okay, right? And when you take dot product here, you get t squared times 0, which is just 0 plus 0 dt plus I have here 1 plus 0 dt, right? So this was, yeah, y squared is 1 squared, and then 2xy is just 2t. Okay, so when you multiply it out, you get 1 plus 0. The first integral gives me 0. The second integral is just integral of t dt, which is just t, 0 to 1, and this is again 1. So what we have seen is then we have computed the work done by the same force along different paths, and along each path we obtain the same amount of work, which is 1 unit, right? Each work is just 1 unit. We use the same force but along different paths. Therefore, in general, we should expect the work to be done to be different along each path, but in this case, they all turn out to be the same. Okay. Sorusu olan var mı? Hı. Soruda veriliyor. Şurada. F is this. Ha yok yok, bu componentları. Yok. Okay. Yeah, this notation is not that great in that sense. So here F1, F2 are just the components of this vector field. Yani F1 y squared, F2 2xy. Tamam. Daha öncekilerde de F1, F2, F3 onlar componentları, türevler değil. That's why actually I prefer f sub x, f sub y to denote the derivatives. But sometimes this is also problematic. I mean, you have to be just careful, okay? Which notation you are using. Yeah, but that's a good point. I mean, it's important, of course, if you take those as the partial derivatives, then you get completely different thing. Okay, let's do another example. Let f x y to be this again plane. So this is y times I minus x times j. So this is just y comma minus x, and we are asked to find f dot dr from 1 0 to 0 minus 1 along two different curves. First, the straight line uh, segment from these points, joining these points, and the second one, 3/4 of the circle of unit radius centered at the origin and traversed counterclockwise. Okay, so let's see what we are asked. Okay, so şöyle çizeyim. Okay, now from this point 1 0 to 0 minus 1 1 0 and then 0 minus 1. One of them is the line segment joining these two, so it is this curve. Let me say this is C1, and the other one is the part of the unit circle joining this point to this point, 3/4 of that, meaning that it is just this curve. Okay, so C2 is this curve, okay, from this point to this point. Just counterclockwise, okay, counterclockwise is this, yeah. All right, and F was what? Fxy was, okay, y comma minus x. All right. So, huh. Şey diyor burada, from 1 0 to 0 minus 1. Both of them are from 1 0 to 0 minus 1. Okay. So I am going from this point 1 0 to 0 minus 1 in two different ways. One of them is this shortcut, the line segment. The other one is the long curve, which is part of the circle. Okay, now first let's compute the integral over C1. So I need a parameterization for this curve, xt, yt. You see, the line segment joining these two points has the equation. What is the equation? So this is the line with intercepts x equals 1 and y is minus 1. So this is just x minus y equals 1, right? This line is just x minus y equals 1. So I can just let, for example, xt to be t, and what is y is then? Y is just t minus 1, right? Because x minus t is just 1. So if I let xt to be t, then I should let y to be t minus 1, because y is just x minus 1. And here from t goes from where to where? Okay. Burada t sıfırdan 1'e değil ama, right? If you choose t from 0 to 1, that's not correct because when you plug t equals 1, 0, you get x equals 0, but x should be 1. So maybe I can do the following. Let t to be 1 and x to be 1 plus t. Yes. Şimdi hani t'ye 0 verdiğinizde bu noktada olmalısınız. When you plug t equals 0, you should be at this point. And when you plug t equals 1, you should be at this point. Therefore, uh, the previous one is not the correct parameterization. I should choose something like this. Tamam mı? Bunu ters yaparsanız o zaman negatifini bulursunuz. Çünkü hani aynı yolu tersten gidiyorsunuz demektir. O da yapılan iş neyse onun eksilisini bulursunuz. So, integral over C1 f dot dr is then what? Integral from 0 to 1. F is just, okay, y comma minus x. What is dr? Dr is the derivative of this. Derivative is just d, so 1, 1, and then dt, right? So this is my xt, and this is my yt. So I have x prime t, y prime t. So this is just, and of course, 0 to 1. Y is just t, and x is 1 plus t, so minus x is just minus 1 minus t. Dot product 1, 1, and then I have dt. So I just plug values of x and y in terms of t also. So we get 0 to 1. When you take the dot product, you get t plus minus t minus 1 dt. So this is just 0 to 1, just minus 1, right? Dt. So this is minus t 0 to 1. So we get minus 1. So the work done by this force is just minus 1 units. Okay. Bir dakika. Yanlış mı yaptık? Şurada sanırım hata yaptım. Y yerine t yazınca x t artı 1. Bir dakika ya. X eşittir 1 artı, bu yanlış mı? X eşittir, şimdi 1 0 doğru. Y yerine t yazdık. Y t eşitse y t'ye eşitse x de 1 artı t. T yerine 0 yazdığımda pardon. Bu da yanlış tabii ki. Şimdi bakalım. T yerine 0 koyarsam 1'e 0, ama t yerine 1 koyarsam 0'a 1 olmuyor. O yüzden şöyle yapmak lazım. Okay, this is not correct either, right? I should be more careful. Here maybe I should say 1 minus t and minus t. Evet. Yani x eşittir 1 artı y. T yerine 0 yazarsam when I plug 0 for t, I get 1, 0. When I plug 1, I get 0, minus 1. Yeah, this should be the correct parameterization. I am sorry. So when you take derivative, you get minus 1, minus 1, minus 1, minus 1. So you get minus this, and then you have this. So you get plus 1 here, plus 1 here, and plus 1 here. 1 dt. Tamam. Neyse şeyi de görmüş olduk. Yani göründüğünden daha karmaşık olabilir. Dikkatli olmak lazım. Let me stop now and do the rest in the second hour.